So, now we have already discussed about the problems of learning bridges if they are connected in loop. So, for that we have to facilitate the bridge with an algorithm which is called the distributed spanning tree algorithm. So, we will try to see how this distributed spanning tree algorithm has been devised and how the bridges in a distributed fashion learn by themselves what should be the corresponding spanning tree. Okay. So, let us try to understand the definition of spanning tree. So, basically spanning tree is if you have a kind of mesh network. Okay, so take a particular network connectivity. Okay, they have some connectivity which is not loop free. Okay, let us say this kind of connectivity we have, it has multiple loops as you can see. So, now if we wish to make this to be loop free, but we have to also span the entire network. That means, suppose this is a particular graph we have taken, it is of course a network. So, it is a graph which is graph is nothing but some set of node and some set of arc. Okay. So, let us say I name them 1, 2, 3, 4, 5, 6. So, that is the bridge IDs let us say and the connectivity between them. So, this node set will be nothing but all the nodes. So, 1, 2, 3, 4, 5, 6. So, those and the arc set will be all the connectivity between them. So, like link 1 to 6, okay, this one, then link 6 to 4 and so on, all the links you list. Okay, so, every link 1, 2, 3, 4, 5, 6, 7, 8, all 8 links. So, 6 nodes and 8 links, that makes the whole graph. Okay. Now, from this graph we have to construct a tree structure where there is no loop, but we have to span the entire network. That means, every node means whatever link will be taking, all nodes should be there and they must be connected via some links. Okay. So, if I take it this way, let us say I take 6, 1, 2, 3, 5 and 4 and I give a connectivity like this. I take this link, I take this link, I take this link and this link. So, that is a spanning tree. So, why it is spanning tree? Because as you can see, I have taken a subset of this graph where this subset is all the node set should be there, the entire n should be there and some a dash, where this a dash is a subset of a. So, that means some of the subset of the links I have chosen such that in this new graph there are no loops. If this happens, then this is called the spanning tree of the other network or other graph. So, that is what we will have to construct. My algorithm should now construct a spanning tree from this particular graph. That means, it should span the entire network. So, all the nodes should be included, but I must take a subset of nodes so that all the nodes are connected. As you can see, these nodes are all connected from any node, starting from any node I can reach to other nodes via all those links. So, basically it is a connected graph. If I would have not taken this one, then it is a disconnected graph, that is not a spanning tree. Okay. So, it must be constructing a tree structure. So, everybody is connected to each other, but they means and also we should ensure that all the nodes are taken into account, then it is called spanning tree. Now, among this spanning tree we can also have a concept of minimum spanning tree, MST. So, minimum spanning tree means if now these links are having some cost value. Okay. So, if I just say this is 1, 2, 3, 1, 5, 7, 10, 11, something like that. If I give the cost value, now I have to construct, or now minimum spanning tree is a unique one. Okay. In most of the cases that will be the case, there might be some tie, but it will be some set of links which I will be taking. It will still construct a spanning tree, but overall link cost, added link cost will be minimum among all possible, means all possible spanning tree that I can construct, because over here as you can see multiple spanning tree I can construct, among them the link cost should be minimum. Suppose if you see, I can also have a spanning tree like this. Instead of taking this link, I could have taken this link and this link I could have taken out. Okay, this is there, assume. This is also a spanning tree because all the nodes are connected, this link only I have taken out. Okay. If I do that, immediately you can see, instead of this link 5, I have now included another link which is costing only 1. So, therefore, this cost is much lesser than, or at least 4 unit lesser than the previous cost. So, like this a minimum spanning tree also can be constructed depending on the cost of these values. Okay. And generally there are some postulate which can be proven, we will not be doing that over here, that how many number of links has to be taken to construct a spanning tree, that is always fixed. As you can see, as many nodes are there, one less link has to be there. So, spanning tree will always have that many number of links. So, that is always true. Okay. So, always I can replace link by another link, because all spanning tree will have eventually same number of links, link by link whichever is the cheapest. So, cost effective or minimum cost spanning tree I will be able to construct. So, there are algorithms to construct these kind of things. Now, you will be asking, what is this cost? What do I mean by the cost of the link? So, cost of the link might be the actual cost of the link, that suppose you have leased this link, okay, or this might be the lease of that LAN, using that LAN. If you try to forward data using that LAN, you might have to pay some cost. So, it might be that cost, of course, it is the economic cost. It might be other things also, cost might be inversely proportional to the delay. So, in that LAN suppose a huge amount of traffic is there, so therefore, delay is little higher. So, you can make that LAN least costly, because you do not want to include that in your network, because that will increase your delay. So, therefore, like that you can devise the cost. Okay. So, it might be inversely proportional to delay, sometimes it might be just the number of hop. So, every link is cost only 1. If the link cost is all link costs are 1, that means they are all uniform. So, therefore, minimum spanning tree will be equivalent to any spanning tree, because number of links are always fixed in spanning tree. So, you will be taking only this many links, and then any one you take, you replace this one by this one, it is still the same cost, because each of the link is costing 1 unit only. Okay. So, how many links you are taking, if that is the cost, or each link is costing only 1, then any spanning tree is minimum spanning tree. Okay. So, the cost is dependent on how do you decide your cost. If it is related to delay, then separate cost might be there. If it is economic cost, then separate cost might be there. If it is just hop count, then only one cost unit per link will be coming into picture. So, depending on that, your spanning tree algorithm will be devised. So, whatever the cost be, that is something which will be a metric which will be given. So, every graph, each link will have its associated cost. So, this will be supplied to you, and with that supply you will be now deciding about your cost. So, the example for spanning tree algorithm that we will be devising, for the time being, of course, any generic cost we can take, for the time being we will take hop count as the cost. Okay. But it can be generalized to any other cost factor. Okay. So, now let us try to see how do we devise this particular kind of protocol. So, that should be our next target. So, for devising this particular kind of protocol, you need to remember that there are two issues. One is this has to be done distributedly. So, basically each of the station must take its own responsibility to decide these things. And how do they decide? Because it is still a centralized things. The spanning tree is spanning over the entire graph. So, every node of the graph must know which link to be activated. Okay. But they should collaborate towards finding a unified spanning tree. If one node thinks that this must be my spanning tree and other nodes decide another spanning tree, then they will be clashing with each other. So, that will not actually be loop free, then they will again create loop. So, therefore, they must collaborate also. So, it is a distributed decision, but it must be collaborative unique decision that must come out. Okay. So, that is why they must be, or there must be some provision of message passing among themselves, and with those messages only they will be deciding, or they will be running their algorithm, and through that they will be uniquely coming out with a unique solution. Okay. So, in a distributed manner, in a unified manner also, they will be coming to a unique solution. That is what we want to see. So, therefore, we need to first understand what kind of message they will be passing among each other. So, the protocol that I will be describing, that is of course that comes from the original centralized protocol of Prims and Kruskal's, whatever greedy approach in spanning tree you can take, because it has an underlying theory that any greedy approach is good for spanning tree algorithm or minimum spanning tree algorithm. So, it comes from that particular viewpoint, and this was devised by Radia Perlman. And you can find it in her book only, the book I am following. So, it is called Interconnection. Bridges, routers, switches and internetworking protocols. Okay, Perlman, it is not A. PERL. Okay. Interconnections, bridges, routers, switches and internetworking protocols. So, it is and she only has devised this protocol. So, this which has been in use. So, we will start describing what was the message that she started thinking about and how those messages helps to build the whole protocol. Okay. So, each bridge locally has to just decide over here, as you can see, each bridge has to decide which node or which LAN he takes for forwarding the packet and which LANs he actually do not forward packet. Okay. So, over here, as you can see, this is the connectivity. So, there are 6 bridges. So, 1, 2, 1, 6, 4, 5, 3 and 2, and all these 6 bridges are connected to all these 8 LANs that we have constructed, and among them let us say bridge 2 decide to utilize this LAN for forwarding, but not this LAN for forwarding. So, this is how they decide it. Okay. Similarly, bridge 4 decide this LAN to forward packet, this LAN to forward packet, but not this LAN to forward packet. Okay. So, they will have to just in a distributed fashion, they should take unified decision, that is all we need to do, and they should take this decision which LAN to forward and which LAN not to forward. So, whenever the packet comes over here, they will always decide not to forward to a particular LAN, they will never do that. Okay. So, their learning will also have this additional learning mechanism. So, even though they have LANs in different ports connected, some of the LAN they will decide not to forward packet. So, they will decide that these LANs, any packet that comes, I will never forward, I will never, whatever packets are coming in that particular LAN, I will never learn them also. So, which stations are connected over there, I will never learn that. Only the path or the LANs I have decided that this must be the designated LAN or this must be the LAN where I will be forwarding my packet, there only I will continue learning my things, like the learning bridges, because once it is a tree he can start learning. So, this is a tree structure, this structure is a tree structure, now he can learn, he will be learning, see this particular LAN he will not learn, this LAN he will learn which stations are connected. from this LAN whatever will be forwarded through bridge will come to him, he will also learn which stations are connected beyond that. So, all these things he will learn, but he will stop learning on those discarded LANs. Okay. So, this is what we want to facilitate, and we try to see how this was done by Radia-Pardon. Okay. So, for that she decided there must be some messages. So, what are those messages? So, the first message is called the root ID. Whoever has done little bit of data structure, or whoever has done little bit of graph theory, in any tree you can always define the tree with a root, and then all others are branches of that. Okay. And then from root it comes to a child, and then from there next set of child, and so on. A tree will never have loops, so it will always be having branches. So, that is why it is called tree. So, basically tree as if like it has a root, and from that root it has branches, again next child, from there branches, some branches might be there, some might not be there, and so on. It just goes on like this. Okay. Not necessarily a binary tree, it can have multiple branches also. Okay, something like that. So, that should be the tree. Always it is like this, and there should be a root from where it all starts. Okay. Even a linear this thing, that also I can decide this to be tree, these two are branches, then it comes over here, from there another branch, and so on. So, basically it just keeps on going from one branch to another branch, or leaf to another leaf, and so on. Okay. So, therefore, there is a concept of root. I can decide, and in a tree anything you can decide as root. So, I can decide this to be root, and then from there I can start taking branches. So, basically anybody can be root. So, this root ID therefore is a very important thing, which has to be encoded in the message. So, that is the first thing. Then the bridge ID. So, bridge ID is whichever bridge is transmitting that message, because we are talking about what message they can pass. So, whenever somebody is passing some message, at that time he has a belief that this must be the root, and this is my bridge ID. So, he is transmitting. So, therefore, he will suppose he is transmitting and he believes this is the root. So, he will give his ID as root ID and his own ID as bridge ID. In the message he will encode these two things. What are the third things? Third thing is the cost he has estimated so far to the root. Okay. In the message, what she has proven, only if these three things we take, it is good enough. If they keep on updating these things in a recursive fashion, it is good enough that after some times they will learn locally and globally, and they will learn the same thing. They will come up with the same tree structure, spanning tree structure. So, let us try to see how it is being initiated. So, basically every node has to pass this message to his neighbor. So, he will be connected via some port. So, let us say if this is the situation, then he has to pass this message to all his neighbors. So on, he has to also pass this message to all his neighbors. Now, how he construct that message and how he initialize this message, that should be the part of the algorithm. Okay. So, for initialization, every node will assume that he is the root. So, basically whatever his bridge ID, that only he will put in his root ID. Immediately, what is the cost? So, he is the bridge ID, from him he wants to reach to the root, and what is the cost? Cost should be 0, because he is the bridge ID. So, from him to root the cost is 0, because if you can reach him, you can reach the root. So, therefore, the cost is 0. So, that should be the initial message. Everybody has their own bridge ID. Okay. So, that bridge ID they take as root ID and take the cost to be 0 and give it to everybody. Okay. Now, what will be happening then? if everybody is actually broadcasting this to their neighbor, they will be getting multiple copies of such messages from all their neighbors. So, let us say this guy, he will generate his own message with his root ID, his bridge ID as root ID and 0 as cost, but he will also get message from this guy and this guy. What he needs to do is, the next message he will be constructing is by seeing all these messages and comparing this message, and there is a method for comparing these messages. So, by comparing these messages, he will be constructing a new message. Okay. So, from the initialized message, he will be now taking all these information. So, local data he will be taking, it is a locally greedy algorithm. So, that is why you are just taking local data, all neighbors data, not anything more than that. So, those local data you will be taking, compare them with certain rule that we will be discussing. So, you compare them and from there you come up with another message, and then you start again broadcasting those messages among your neighbors, and this has to be done by everybody. And we will be showing by the comparing technique that they will be slowly coming up towards a convergence of a particular structure. So, let us try to see how they compare. So, we have already seen that they have root ID, bridge ID and cost. Now, we have to come up with the unique root ID, right. What happens in the initial, what will be happening? Everybody assumes themselves to be root. If they assume themselves to be root, their ID will be coming as root ID. Now, because they have all unique bridge ID, because it is a MAC ID which is unique. So, if they have these things, I can now compare, and I can say my comparison method will be whoever has the lowest ID, that must be the root. If I declare that, then I know that once the messages are passed from neighbor to neighbor to neighbor, then this root ID will prevail. So, whoever in the entire network has the lowest root ID, that should become the root ID automatically for everybody. So, if I just for comparison take these things, that if two messages I see, among them whichever has lower ID, that must be my means now designated root ID. So, if I compare, my comparison should be like that. So, let us try to see two messages how they can be compared. So, first thing is this root you have to compare. Once you, if there is a possibility that root will be tied. Okay. So, both of them thinks that this is the root. So, it might, how that might happen. So, let us say I have this kind of connectivity. This has a root ID 1, this has 2, this has 3. So, initial message of him, what that will be? That will be, let us say I put the message in this fashion, root ID dot cost dot bridge ID. Okay. So, what will be his message? He thinks his bridge ID is 3. So, root ID is 3, 3 dot 0 dot 3. What will be his message? That should be 0 2 dot 0 dot 2. What will be his message? 1 dot 0 dot 1. Now, he will broadcast this message to both of them. So, now what this guy gets, and he will also broadcast these two messages to both of them, and so on. Okay. Everybody broadcast this. So, everybody they will get 3 messages. One is his own message. So, let us say think about him. So, his message is 101, he gets from his next neighbor 202, and the next neighbor he gets 303. Okay. So, after receiving these 3 messages, if I now compare these 3 messages. Okay. So, what I can see among them root ID wise, if node 1 thinks, he thinks that mine 1 is lesser than these 2. So, therefore, I must be the root. Okay. Now, think about what happens to 2. 2 has his own message 202, and then he gets from his neighbor 101, and from his other neighbor 303. Among them he can see that root ID this one is lower. So, he thinks 1 is root. Now, as you can see they are converging. 1 thinks he is the root, 2 is also thinking that he is the root, for 3 also same thing will be happening. Now, all 3 if they compare in this fashion, they will be coming to a unique conclusion that this guy must be the root, and then they start operating the protocol next. Now, among the messages while comparing, what they do, they try to first see this root ID. It might happen sometimes, suppose after this first iteration what will be happening, 2 and 3 both will be thinking 1 as root. So, now among his messages 2 also thinks 1 is root, 1 also thinks 1 is root. So, if he gets the next message, root will be same. Now, how he discriminate? Now, the discrimination will be cost. So, then he will, if root IDs are same, then he thinks about cost. Whichever has lower cost to root, that must be my, because I want to also go to the root with the smallest possible distance, okay, because it is a minimum spanning tree. So, I want to reach to the root, every node should target to reach to the root with the smallest possible number of hops. So, if hop count is the cost, then smallest possible hop. So, next I will be deciding on cost. If cost in 2 of these messages, whichever is lower, I think that via him only I will be reaching to the root fast. So, therefore, I should take via him as my designated route towards the root, whatever I am thinking. Okay. If even cost are same, that means I see that via this guy also I take 2 number of hops, via this guy also I take 2 number of hops, and both of them go to the same root. So, cost are same, root are same, then among bridge IDs, now that I have to just break the tie somehow. So, I take, because I have to still take unique, so therefore, I take the lowest bridge ID and through them I will route my things. So, that becomes my designated route, the other one will not be, I will be discarding that. Okay. So, therefore, tiebreaker is with this fashion. First you see root ID among the messages, whatever message you have received from others and whatever message locally you have generated, you will be comparing them. So, comparison techniques are, first you do by root ID, then you do by cost, and then you do by bridge ID. So, you see all these 3 things and break the tie, whichever wins, that now happens to be your message. How you construct that message after comparison, we will come back to that later. Okay. So, this is what is the comparison that is being enforced. After this comparison, as you can see, slowly it is building up towards finding a unique spanning tree in a distributed fashion. So, we will come back to the rest of the protocols, that after comparison how do we come up with a message, and then how do I designate the ports as which one should be my designated this one, whose packet I should forward, whose packet I should not forward, who should be in which direction my designated route is connected to. So, all these things how he decides, every node in a distributed fashion, from these messages and this comparison only they will be deciding. So, that part we will be trying to see in the next class.